Okay, so what are we trying to do in this course? Prerequisites, there's programming, discrete math, and probability. So you need to be able to code, you need to be able to do some math and some kind of basic proofs, right? So these are the classes that are required or at least recommended that you, or if you have some equivalent experience, that's fine too. And what should you hope to get out of this course, right? So one hand, the course is meant to be giving you a set of tools. Using the modeling, inference, learning paradigm, it gives you a set of tools and a way of thinking about problems that hopefully will be really useful for you when you go out into the world and try to solve real-world problems. And also, as a side product, I also want all of you to be more proficient at math and programming, because those are kind of the core elements that enable you to do kind of interesting things in AI. So a lot of AI you read about it is very flashy, but really the foundations are still just math and programming in some sense. Okay, so the coursework is homeworks, exam, and a project. That's what you have to do. Homeworks, there's 8 homeworks. Each homework is a mix of written and programming problems centered on a particular application covering one particular type of model, essentially. Like I mentioned before, there's a competition for extra credit. There's also some extra credit problems in the homeworks. And when you submit code, we have an autograder that runs. It's going to run on all the test cases, but you get a feedback only a subset, so you can it's like in machine learning, you have a train set and you have a test set. So don't train on your test set. Okay, so the exam is testing your ability to use the knowledge that you learn to solve new problems, right? So there's and I think it's worth taking a look at the exam, because this kind of surprises people the exam is a little bit different than the types of problems that you see on the homework, and they're kind of more problem solving. So the exam isn't going to be like a multiple choice, like okay, when was perceptrons published, or something like that. It's going to be, here's a real life problem, how do you model it and how do you come up with a solution. They're all going to be written, it's closed book, except for you have a 1 page of notes, and this is a great opportunity to actually review all the material and actually learn the content in the class. So the project, I think, is a really good opportunity to take all the things that we've been talking about in the class and try to find something you really care about and try to apply it. Work in groups of 3, and I really recommend finding a group early. And I emphasize, it's your responsibility to find a good group, right? Don't come to us later, like 1 week before the project deadline, and say, oh, my group members, they ditched me or something. Really try to nail this down. Use Piazza or your other social networks to find a good group. So throughout the quarter, there's going to be these milestones for the project, so to prevent you guys from procrastinating until the very end. So there's going to be a proposal where you try and brainstorm some ideas, progress report, a poster session, which is actually a whole week before the final report is due. And the project is very open. So this can be really liberating, but also might be a little bit daunting. We will hopefully give you a lot of structure in terms of saying, okay, how do you define your task? How do you implement different baselines and oracles, which I'll explain later? How do you evaluate? How do you analyze what you've done? And each project group will be assigned a CA mentor to help you through the process. And you're always welcome to come to my office hours or Dorsa's or any of the CAs to get additional help, either brainstorming or figuring out what the next step is. Some policies, all assignments will be submitted on Gradescope. There's 7 total late days. You can use at most 2 per assignment. After that, there's no credit. We're going to use Piazza for all communication. So don't email us directly. Leave a post on Piazza. I encourage you to make it public if it's not sensitive, but if it's personal, then obviously make it private. And try to help each other. We'll actually award some extra credit for students who help answer other students' questions. So all the details are on the course website. Okay, so one last thing, and it's really important, and that's the honor code. Okay, so especially if you're, you've probably heard this if you've been at Stanford. If you haven't, then I want to really kind of make this clear. So I encourage you all to kind of collaborate, discuss together, but when it comes to actually the homeworks, you have to write up your homework and code it independently. So you shouldn't be looking at someone's write-up. You shouldn't be looking at their code. And you definitely shouldn't be like copying code off of GitHub. That's hopefully should be obvious. And maybe less obvious, you should not, please do not post your homework assignments on GitHub. I know you're probably proud of the fact your Pac-Man agent is doing really well, but please don't post it on GitHub because then that's going to be an honor code violation. When debugging, if you're working together, it's fine to, as long as it's kind of looking at input-output behavior. So you can say to your partner, hey, I put in this input to my test case, I'm getting like 3, what are you getting? So that's fine, but you can't, remember, don't look at each other's code. And to enforce this, we're going to be running MOS, which is a software program that looks for code duplication to make sure that the rules are being followed. And changing one variable name is, or you'll be so, anyway, enough said. Just don't do it. Okay? Any questions about this? I want to make sure this is important, or about any of the logistics. Yeah?
Does the GitHub thing apply to the final project?
The final project you can put on GitHub. Yeah.
You have private GitHub repos,
yeah.
That's totally fine.
Yeah, private GitHub repos is fine. Yeah, question in the back?
Necessary to have a group, or can you do a solo project?
The question is, can you do a solo project? You can do a solo project. You can do a project with 2 people. You can do a project with 3. I would encourage you to try to work in groups of 3 because you'll be able to do more as a group. And there's definitely, it's not like if you do a solo project, we'll be expecting like 1/3 of the work. So, okay, anything else? All right. Okay, so in the final section, I want to actually delve into some technical details. And one thing we're going to focus on right now is the kind of inference and learning components of this course. So I'm going to talk about how you can approach these through the lens of optimization. So this is going to be, it might be a review for some of you, but hopefully it's going to be a good way to get everyone on the same page. Okay, so what is optimization? There's kind of 2 flavors of optimization that we care about. There's discrete optimization, where you're trying to find the best discrete object. For example, you're trying to find the best path, or the path P that minimizes the cost of that path. We're going to talk about one algorithmic tool based on dynamic programming, which is a very powerful way of solving these complex optimization problems. And the key property here is that the set of paths is huge, and you can't just try all of them and compute the cost and choose the best one. So you're going to have to do something clever. The second brand of optimization is continuous optimization. And formally, this is just finding the best vector of real numbers that satisfies or minimizes some objective function. So a typical place this shows up is in learning, where you define objective function like the training error, and you're trying to find a weight vector W. So this notation just means it's a list of numbers, D numbers, that minimizes the training error. And we're going to show that gradient descent is easy and a surprisingly effective way of solving these continuous optimization problems. Okay, so to introduce these 2 ideas, I'm going to look at 2 problems and try to kind of work through them. So this might be also a good way to think about how you might go approach homework problems. Trying to kind of talk through this in a bit more detail. Okay, so the first problem is computing at this distance. And this might not look like an AI problem, but a lot of AI problems have this as kind of a building block if you want to do some sort of matching between two words or two biological sequences. So the input is you're given two strings. I'm going to start writing over here on the board just to work this out. So you're given two strings, S and T. So for example, a cat and the cats. Okay, so these are two strings. And you want to find the minimum number of edits that is needed to transform S into T. And by edits, I mean you can insert a character, like you can insert an S. You can delete characters, like you can delete this A. And you can substitute one character for another, so you can replace this A with a T. Okay? So here's some examples. What's the edit distance of cat and cat? It's 0. You don't have to do anything. Cat and dog is 3. Cat and at is 1. You insert the A or insert the C. Cat and cats is 1. And a cat and the cats is 4. Okay? So the challenge here is that there are quite a different number of ways to insert and delete. Right? So if you have a string that's very long, there's just way too many things to just try out all of them. Okay, so then how do we go about coming up with a solution? So, any ideas? Yeah.
Simplify the output in terms of saying that a substitution can just be considered, or a deletion can just be considered a substitution, or vice versa by saying like an empty character.
Yeah. So let's try to simplify the problem a bit, and building off on what you what was said. So one thing to note is that so the general principle. Let me just write the general principle. Is to reduce the problem to a simpler problem, because that you can hopefully solve. It is easier to solve, and then you can maybe keep on doing that until you get something that's trivial. Okay, so there's maybe two observations we can make. One is that, well, we're technically saying we can insert into S, right? But if we insert into S, it makes the problem kind of larger in some sense, right? I mean, that's not good. That's not reducing the problem. But whenever we insert into S, we probably want to insert things which are in T. We want to cancel something out, right? So we wouldn't insert a K there for any reason. We probably want to insert an S, in which case S matches that, and then we've reduced that problem, right? So we can actually think about inserting into S to S as equivalent to kind of deleting from T. Okay, does that make sense? All right. So another observation we can make is that we can start inserting anywhere. We can start inserting here and then jump over here and do this. But this just introduces a lot of ways of doing it, which all kind of result in the same answer. So why don't we just start more systematically at one end and then just proceed and try to chisel off the problem kind of, let's say, from the end. Okay, so start at the end. Okay, so now we have this problem. I'm going to draw a problem in a little box here. So let's start at the end. Yeah, question?
What was the reasoning that we used to reach that principle, start at the end?
The question is, why are we starting at the end?
Right.
As opposed, well, the idea is that if you start at the end, then you have kind of a more systematic and consistent way of reducing the problem. So you don't have to think about all the permutations of where I can delete and substitute.
Why is it more systematic to go from the right to the left than from the left to the right?
We can also do left to right. So the end or the start is both fine. This is I just picked the end. Yeah?
How do we know starting at one end can give us the optimal strategy?
Yeah, the question is, how do we know that starting at one end can give you the optimal strategy? So, if you wanted to prove this more rigorously, there's some work, but I'll just try to give you a intuitive answer. Suppose you didn't start at the end, and you just made a sequence of steps, like I insert here, I delete here, and then I went over here, and did all those operations to S. I could have equivalently also just sorted those by where it was happening, and then just proceeded from one end to the other, and I would arrive at the exact same answer. So without loss of generality, I can start that. Any other questions? Okay, so yeah.
So instead of doing this, wouldn't the more viable approach be trying to recognize some patterns instead of doing this? I mean, between the two strings, S and T, like some sort of pattern that are included in both of the S and T strings.
Yeah. So the question is, maybe you can recognize some patterns. Wow, it's like, oh, cat. That's maybe those should be lined up. I guess these examples are chosen so that these patterns exist, but we want to solve the problem for cases where the pattern might not be obvious. It could be we want to work for it to work for all strings. Maybe there is no pattern, and we still would want a kind of efficient algorithm to do it. Yeah?
Can we just use dynamic programming? Like we go one by one, there is always basically two steps. Either we're doing substitution, or otherwise it's the same character, or we have to insert.
Yeah.
And then we keep going, and we just remember each two strings that we have at one point, so that if we calculated that, we don't have to do it again.
Yeah.
And that's it.
Yeah. Great idea. Let's do dynamic programming. So that's what I'm kind of trying to build up to. Okay, so if you look at this, so dynamic programming is a kind of general technique that essentially allows you to express a more complicated problem instead of a simpler problem. So let's start with this problem. If we start at the end, if the two match, then we can just immediately delete these two, and it's going to be the same, right? So we can get some free rides there. Okay, but when they differ, now we have many options. So what could we do? Well, we could substitute. Okay, we can change the T to an S. So what does that leave us with? So I can do cats. T is the cat. Okay, so I can substitute. Okay. What else can I do? Someone say something I can do. So I can insert. Insert where? Into. So I can insert an S, right? But that's the same as by one deleting from T. So but I can basically also just delete this S. So this is a cat, and I deleted this S from T. Okay, so this is let's call it I guess let's call this insertion. It's technically insertion. And then finally, what can I do? I can also remove T. So A, K, C, A, T, the cat. Okay, so this is delete. And right now, you're probably looking at this like, well, obviously, you should do this one. But in general, it's hard to tell, right? If I just give you some arbitrary strings, who knows what the right answer is. So in general, how do you pick? Yeah.
The second one, the T is supposed to be the cats.
You mean this one?
Yeah.
So here I inserted an S, right? But then because there's two S's here, I just cancel them out and just left for that. So you can think about this as really deleting from.
We're just not considering. So like in the original problem, we said we're transforming S to T. Right?
Yeah. So I'm because of this, I'm kind of trying to reframe the problem a little bit. Okay, so which one should I choose? Yeah.
What about the substitution the other way?
The substitution the other way, meaning change.
S to T.
Sorry, there's too many S's and T's here, which is unfortunate.
As in replace the last S pass with T.
Oh, you could.
Did we eliminate that, or did we not?
That's, you can think about that as kind of equivalent. So if you identify two letters that you want to make the same, then you can replace the one to be the other or the other to be that. I mean, officially we've been kind of framing it as we're only editing S, which is the reason that it's asymmetric. Okay, so which one of these? Door A, door B, or door C? Yeah.
Would you look for similarity then between S and T at every step, and then you pick the middle one because there's cat in both of them?
Yeah, so you could try to look inside, but remember these might be really complicated. So we want a kind of a simple mechanized procedure to tell.
What about the next letter?
The next letter. Yeah, let's pretend these are you can't see inside them. Okay.
Keep going with each of the different cases.
Yeah, okay, so let's keep on going. So I'm not going to draw everything, but you can also try to break this down into maybe there's 3 actions here and 3 actions here, right? And at the end of the day, you hopefully have a problem that's simple enough that where S equals T or something, then you're done. But then, how do I know? Suppose I've solved this. Suppose someone just told you, okay, I know this cost, I know this cost, I know this cost. What should you do? Yeah, you should take the minimum, right? Like remember, we want to minimize the edit distance. So there's 3 things you can do. Each of them has some cost of doing that action, which is 1. Every edit is the same cost. And then there's a cost of continuing to do whatever you're doing. And so we're just going to take the minimum over those. Yeah.
How do we know that that's like the optimal amount of moves that we have to take?
Yeah. So I was trying to argue that if you're going to right to left, it's without lots of generality. Because if you went left to right or in some other order, you can also replay the edits in order.
Strings that are like the difference is 1 letter that you needed 1 insertion on like the top left and like the top string. But if you're going from right to left, it looks like as if they're all shifted over by 1. Or no, if you start.
Yeah.
Oh, that would work. Okay.
Yeah, I think it works. Okay, so let's try to code this up and see if we can make this program work. Okay, so I'm going to do edit distance. Can everyone see this? Okay, so I'm going to define a function. It takes 2 strings. And then I'm going to define a recurrence. So recurrences is I guess one word I haven't really used, but this is really the way you should kind of think about dynamic programs and this idea of taking complex problems and breaking it down. It's going to show up in search problems, MDPs, and games. So I guess it's something that you should really be comfortable with. So let's define a recurrence as follows. So remember, at any point in time, I have, let's say, a subproblem. And since I'm going right to left, I'm only considering the first M letters of S and the first N letters of T. Okay, so recurse is going to return the minimum edit distance between 2 things, the first M letters of S and the first N letters of T. I'm going to post this online so you guys don't have to try to copy this. Okay, so suppose I'm going to define this function. If I have this function, what should I return? Recurse of. So M is an integer, right? So N is an integer, so I'm going to return the length of m and the length of n. Okay, so that's kind of the initial state. Sorry. Yep. Okay. All right. So now I need to fill out this function. Okay. So let's consider a bunch of cases. So here's some easy cases. Suppose that m is 0, right? So I have comparing an empty string with something that has n letters. So what should the cost of that be? I heard some rumbling. It should be n. And symmetrically, if n is 0, then result should be m. And then if now we come to the kind of initial case that we consider, which is the ends actually match. So if s, the last letter of m, this is zero-based indexing, so that's why there's a -1. So if this matches, then what should I do? So now I reduce this to a subproblem, right? So I have n-1, n-1. Okay? And now comes the fun case, which we looked at. So there's, in this case, the last letter doesn't match, so I'm going to have to do some sort of edit. Can't just let it. Yeah, question.
Would it be worth doing a full S to T compare, or S through M and then T through N compare?
Would it worth doing a full STE compare?
Rather than waiting until, I guess,
yeah.
doing like the last letter match.
There's probably a way you can make this more efficient. I'm just going to try to get the basic thing in there. Okay, so substitution. Okay, so what's the cost of a substitution? I pay 1 to do the substitution, and as a reward, I get to reduce the problem to n-1 and n-1, right? So I lop off a letter from S and I lop off a letter from T. So what else can I do? So I can delete. So that also costs 1. And when I delete from S, and then n, so this remains the same. And then now you can think about the insertion is n-1. Right, because remember, insertion into S is deletion from T. That's why this is n-1. Okay, and then the result is just going to be a minimum of all of these things. Okay, return result. Okay, so just, and then how do I call this function? A cat, the cats. So let me print out the answer. Let's see if it works. Okay, print out 4. Therefore, I conclude it works. No. I mean, if you were doing this, you would probably want to test this some more, but in the interest of time, I'll kind of move on. So let me just kind of refresh. Okay, so I'm computing this edit distance between 2 strings, and I'm going to define a recurrence that works on subproblems, where the subproblem is the first m letters of S and the first n letters of T. And the reason I'm using integers instead of strings is to avoid like string copying implementation detail, but it doesn't really matter. So base cases. So you want to reduce your problem to a case where it's trivial to solve. And then we have the last letter matches, and then we have the letter doesn't match, and you have to pay some sort of cost. I don't know which action to take, so I'm going to take the minimum of all of them. And then I call it by just calling recurse. OK, so this is great, right? So now I have a working thing. Let's try another test case. So I'm going to make this. So if I do times 10, this basically replicates this string 10 times. So it's a long string, longer string. OK, so now I'm going to run it. Maybe I shouldn't wait for this. There is a base case. I think it works, but it's what's wrong with this code? Yes, it's very slow. Why is it slow? Yeah, right. So I'm recursing every point recurses 3 times, so you kind of get this exponential blow up. So there's kind of a, how do you solve this problem? Yeah, you can I think I heard the word memoize, which is another way to kind of think about memoize plus, I guess, recurrence is dynamic programming, I guess. So I'm going to show you kind of this way to do it, which is pretty uninvasive. And generally, I recommend people, well, get the slow version working, and then try to make it faster. Don't try to be too slick at once. OK, so I'm going to make this cache, right? And I'm going to say if mn is in the cache, then I'm going to return whatever's in the cache. So the cache is just a dictionary mapping the key, which is identification of the problem I'm interested in solving, and the result, which is the answer that I computed. So if I already computed it, I don't need to compute it again, just return it. And then at the end, if I have to compute it, then I have to put this in the cache. OK? So 3 lines, or 4 lines, I guess. Yeah.
Wouldn't you want cache outside the recurse function?
Yeah, that's a great point. This should be outside the recurse function. Yeah, glad you guys are paying attention. Otherwise, yeah, it would do basically nothing. Any other mistakes? Yeah.
There are some function decorators that implement memoizing for you. In this class, are you okay if we use that, or would you rather us make our own in this case?
You can use the you can be fancy if you want.
Okay.
Yeah, but I think this is pretty transparent and easy for learning purposes. OK, so let's run this. So now it runs instantaneously as opposed to I actually don't know how long it would have taken otherwise. OK, and sanity check 4D is probably the right answer because there's 4 was the original answer and multiplied by 10. OK, any other questions about this? So this is an example of kind of basic dynamic programming, which are you solve a problem trying to formulate it as a recurrence of a complicated problem in terms of smaller problems. And like I said before, this is going to kind of show up over and over again in this class. Yeah? Yeah, so the question is, why does this reduce redundancy? Is that right? So maybe I can do it kind of pictorially. If you think about, let's say you have a problem here, right? And this gets reduced to, I'm just making kind of an arbitrary diagram here. So this problem gets reduced to these 2, and this problem gets reduced to these 2, and so on. Right? So if you think about if you didn't have memoization, you would just be paying for the number of paths. Every path is a kind of you have to compute from scratch. Whereas if you do memoization, you pay in the number of nodes here, which a lot of this is shared. Like here, once you compute this, no matter if you're coming from here or here, you're kind of using the same value. OK, so let's move on. So the second problem we're going to talk about has to do with continuous optimization. And the motivating question here is how do you do regression, which is a kind of a bread and butter of machine learning here. So here we go. Regression. OK, so imagine you get some points. OK, so I give you a point, which is 2, 4. And then I give you another point, let's say 4, 2. And so these are data points. You want to, let's say, predict housing price from square footage or something like that. You want to predict health score from blood pressure and some other things. So this is pretty common in machine learning. And the question is, how do you fit a line? I'm going to kind of consider the case where your line has to go through the origin, just for simplicity. So you might want to like find a fit. I mean, 2 points is maybe kind of a little bit degenerate, but that's the simple example we're going to work with. In general, you have lots of points, and you want to fit the line that best kind of is close to the points. Okay, so how do you do this? So there's a principle called least squares, which says, well, if you give me a line, which is given in this case by a slope w, I'm going to tell you how bad this is. And badness is measured by looking at all the training points and looking at these distances, right? So here I have, this particular, let's say point, xi. If I hit it with w, then I get basically the, the y-intercept here, not the y-intercept, but the y value here. That's my prediction. The real value was yi, which is up here. And so if I look at the difference, I want that difference to be 0. Right? So in least squares, I square this, and I say I want this to be as small as possible. Right? Now this is only for 1 point, so I'm going to look at all the points. Let's suppose I have n points, and that's a function that I'm going to call f of w, which basically says for a given weight vector, which is a slope, give me a number that characterizes how bad of a fit this is, where 0 means that I fit everything perfectly, and large numbers mean that I fit it poorly. Okay. All right, so that's regression. So how do I solve a regression problem? So how do I optimize this? Can you do this in your head? So if I actually had these 2 points, what should W be? Okay, doesn't matter. We'll compute it. So how do we go about doing this? So one principle, which is maybe another general takeaway, is abstract away the details. Right? This is also true with the dynamic programming. But sometimes, you get, if you're too close to the board and you're looking at, oh man, these points are here and I need to fit this slide. How do I do that? You kind of get a little bit stuck. But why don't we think about this f as, say, some function? I don't really care what it is. And let's plot this function. Okay, so now this is a different plot now. This is the weight, and this is f of w. Always label your axes. And let's say this function looks like this. Okay. So which means that for this slope, I pay this amount. For this slope, I pay this amount, and so on. And what do I want to do? I want to minimize f of w, which means I want to find the w which has the least value of f of w. Right? Question?
Derivative.
Okay, so you take the derivative. So what does the derivative give you? It tells you where to move, right? So if you look over here, so you can't, in general, you might not be able to get there directly. In this actually particular case, you can, because you can solve it in closed form, but I'm going to try to be more general. So if you start here, this derivative tells you, well, the function is decreasing if you move to the right. So then you should move to the right. Whereas over here, if you end up over here, the derivative says, the function is decreasing if you move to the left, so you should move to the left. Right? So what I'm going to introduce is this algorithm called gradient descent. It's a very simple algorithm. It basically says, start with some place, and then compute the derivative, and just follow your nose. Right? If the derivative says it's negative, then just go this way. And now you're at a new point. And you compute the derivative again. You descend, and now you compute it again. And then maybe you compute the derivative and it says keep on going this way. Maybe you overshoot, and then you come back, and then hopefully you'll end up kind of at the minimum. Okay? So let's try to see what this looks like in code. So gradient descent is one of the simplest algorithms, but it really underlies essentially all the algorithms that people use in machine learning. So let's do points. We have 2 points here. And I'm going to define some functions. Okay, so f of w. So what is this function? So I'm going to sum over all the different, and basically at this point it's converting math into Python. So I'm going to look at all the points. So for every xy, what the model predicts is w times x minus y. And if I square that, that's going to be the error that I get on that point. And then if I sum over all of these errors, then I get my objective function. Okay? Array of, yeah, so you can put array here if you want, but it doesn't matter. It's actually fine. Okay, so now I need to compute the derivative. So how do you compute the derivative? So if your calculus is a little bit rusty, you might want to brush up on it. So what's a derivative? Remember, we're taking a derivative with respect to w, right? There's a lot of symbols here. Always remember what you're taking a derivative with respect to. Okay, so the derivative of the sum is the sum of the derivative. So now I need to take the derivative of this, right? And what's the derivative of this? Well, something squared, you bring the 2 down here, and now you multiply by the derivative of this. And what's the derivative of this? Should be x, right? Because this is a y, this is a constant, and w derivative w times x with respect to w is x. Okay, so that's it. Okay, so now let's do gradient descent. Let's initialize with w equals 0, and then I'm going to just just iterate 100 times. Normally you would set some sort of stopping condition, but let's just keep it simple for now. Okay, so for every moment I have a w. I can compute the value of the function, and I also take the gradient or the derivative. Gradient just means derivative in higher dimensions, which we'll want later. Okay, and then what do? I take w and I subtract the gradient. Okay, so remember. Okay, I'll be out of. Yeah. So I take the gradient. Remember, I want to have the gradient. Gradient tells me where the function is increasing, so I want to move in the opposite direction. And eta is just going to be this step size to keep things under control. We'll talk more about it next time. Okay, so now I want to do print out what's going on here. So iteration, print out the function, and t value. Okay. All right, so let's compute the gradient. And so you can see that the iteration, we first start out with w equals 0, then it moves to 0.3, and then it moves to 0.7999999, and then it looks like it's converging to 0.8. And meanwhile, the function value is going down from 20 to 7.2, which happens to be the optimal answer. So the correct answer here is 0.8. Okay, so that's it. Next time we're going to start on the machine learning lecture.